It all started with the Wright brothers.
Man's age-old dream of flight becomes a reality.
The world became more connected.
Passengers, British airliners.
Important stepping up.
Yet it also contributes to a serious problem.
We're facing a man-made disaster of global scale.
There is a solution. We are AeroDelft.
Good evening, partners, team members, alumni, students, friends, and family. Thank you all for coming. It is my privilege to welcome you to the AeroDelft summer event. We gathered here tonight to celebrate some of the biggest achievements AeroDelft has ever seen. We are closer than ever in achieving our mission to prove and promote that liquid hydrogen is an alternative to conventional fuels in aviation. This also ties in the program of tonight, where first our Chief of Partnerships will tell you about the operation side of AeroDelft, thereby showing how far we've came with the to promote part of our mission. This is followed by presentations by our engineering chiefs and technical managers who will walk you through the engineering work done this year, showing how far we've come with the to prove part of the mission. But first, just like the video, let's take a step back to the very origins of AeroDelft to see what led to the inception of AeroDelft, Project Phoenix, and to where we are today. As long as mankind existed, we have always dreamt of taking off to the skies. About 120 years ago, this dream finally became a reality. The Wright brothers achieved the first ever manned motorized flight. Let this sink in for a bit. By pushing the boundaries of what's possible and with a true feat of engineering, we humans gain the ability to fly. This truly revolutionized transport the way we knew it. However, as many of you also might know, there's also a darker side to this. Climate change. This is an issue we cannot understate. We all know it is here, we all know it is a problem, and we also all know who caused it. Us, people. Us, people. We all together have to drastically change the way we see what we do. Whether you like it or not, we all contributed to climate change during the course of our lifetimes. Our choices, our actions, our lifestyles have all led to an increase in greenhouse gas emissions. Of these greenhouse gas emissions, about 25% comes from the transport sector. Of this 25%, 12% comes from aviation. I already hear you thinking, oh, that's not that much, right? Well, if you look at our next slide, you see that since 1990, the carbon footprint of the aviation industry more than doubled. This is partly because the aviation industry almost experienced no carbon restrictions, while other sectors often had to adapt. Today, driving by car in a carbon-neutral way is a reality, while aviation seems to be lagging behind. The aviation industry, evidently, is the quickest growing sector with a carbon footprint there is. On top of that, by 2050, the demand for aviation is expected to triple. Clearly, something has to change. Incremental evolution in the form of efficiency savings is not enough. We have to radically rethink the way we propel our aircraft. This is what led to the foundation of AeroDelft and soon after Project Phoenix, the name marking the rebirth of the aviation industry. It was a team of 2018 who first set up this project and its mission and vision. They were also the first who focused on gliders and liquid hydrogen. I also hear you thinking, but why hydrogen? Well, compared to kerosene, the use of hydrogen does not lead to an increase in CO2. The only byproduct is water. Also, when we make this liquid, we can also store it in a much smaller and compact way. This makes it one of the most promising alternatives to decarbonize aviation. With this new focus on liquid hydrogen, the 2018 team really got us off the ground. The subsequent 2019 team were the first to start the production of our Phoenix prototype, as you can also see on the slide right here. But as many of you also know, in this academic year, so 1920, was also the year where the COVID-19 pandemic struck. Despite the countless challenges this brought with it, like working online or not even having a workshop, this team pushed through, even throughout the summer holidays, in a shed in Belgium to keep building this aircraft. The team before us made significant strides in growing AeroDelft as an organization. They were also the one to first build, finish, and reveal the first tangible milestone of AeroDelft ever, the structure of the Phoenix prototype, as you can also see right here in this beautiful aircraft. On top of that, they also acquired the aircraft parts for a next step of Project Phoenix full scale. They also facilitated AeroDelft's move to the TU Delft aircraft hall, increasing our connection with them. This led to our team. I cannot stress enough what an honor it is for us to take up their mantle in such a stage. Not only were we tasked to achieve one of the biggest dreams AeroDelft has ever had, we also had the privilege to build, develop, and reveal the building of the Phoenix full scale. Blood, sweat, and tears brought us to this very moment. Me standing before you with my dear team members, where we get to show all of our big achievements of the whole year to all of you. It brings me great joy to see so many of you in the room as well. Back when I just started, I could have never foreseen what we would achieve and how quick and how much the growth of AeroDelft would be in 1 year. It is my privilege to introduce our Chief of Partnerships, Joseph Michaels, who will talk about this growth in AeroDelft and where we fit in the aviation landscape.
Thanks, Rahik, and thank you for the great introduction. Many of you might be wondering how exactly AeroDelft fits into the wider and more mature aviation industry. And that's what I want to talk to you about today. AeroDelft prides itself in its student team and non-profit structure. It's what lends us both the abundance of engineering talent along with the flexibility that we need to navigate into a net zero aviation industry. Naturally, working with liquid hydrogen, specifically in the aviation industry, leads us to working with companies across the entire sector. We work with all corners of the commercial world, from finance to engineering, component manufacturers, the list goes on and on. Thousands of business cards later, I'm happy to announce that we are now working with 50 active partners, 20 of whom we've added over the last year. Now, partnerships to AeroDelft are more than just a name on the aircraft in exchange for funding, but we really work with our partners towards our end goal, and we collaborate along the way. Now, we can put our partnerships down to 3 separate areas: co-development, education, and the implementation of young talent. Let's start off with co-development. Now, in the hydrogen industry, specifically the liquid hydrogen industry, and especially the liquid hydrogen aviation industry, we're somewhat of the first people to do it, among others. This means we cannot really buy off-the-shelf components, and the majority of what we need to build our products has to be developed in-house or with a partner. Now, this creates an excellent opportunity because we work with our partners to co-develop these technologies, which not only keeps our progress high, but it also accelerates our partners' development from the idea and concepts to having a final product that is ready for the mass market. Next, moving on to education. A lot of us are brand new to this topic. We've not built planes before, we've not worked with cryogenics, we've not worked with hydrogen, and some of us have not stepped or dipped our toes into the commercial world. So it really is a first for many of us. What we're learning at AeroDelft cannot just be taught in a classroom, and these are practical skills that need to stick with us for the rest of our lives as we go on into our careers. And with sustainability at the heart of everything we do at AeroDelft, these values also, we hope, stick with our current students and our future alumni and takes with them to their future careers and lives. Finally, with young talent. Student teams, and specifically AeroDelft, act as a bridge between the corporate world and students. Now, this works great for both of us because you have the students with our out-of-the-box thinking, which really benefits our partners who might have a bit of tunnel vision if you've worked so long in the industry. And then back from our partners, our students get a harsh reality check, and then this helps us come to a compromise and we have an end product. We've already seen the benefit of young talent being implemented into industry, with many of our alumni already doing placements, internships, or even finding full or part-time positions at our partnering companies. Now, as I mentioned, building liquid hydrogen aircraft is a tough feat. And we need to work with people all around the world to do so. Now, aerospace being arguably one of the most international industries, and with the only way of really tackling climate change being through global cooperation, our international ties are an absolute must. And this year, our involvement with the industry has gone larger than ever before, as we're now looking into the feasibility of constructing hydrogen infrastructure. Now, behind the scenes of AeroDelft is our small and often overlooked operations department. We're a team of 8 people spread across partnerships, legal, graphics, and exposure. And not to forget our amazing operations manager, Ivy. Now, expanding our reach, the Partnerships Department, Ishan, Gregoire, and I, along with various engineers, have begun to attend events, visit partners, and make speeches all across the Netherlands, even expanding across to our neighboring countries in Belgium and also Germany. We've gone as low as Friedrichshafen, as far as Berlin, and as high as Sweden, all in our pursuit of proving and promoting liquid hydrogen in aviation. Every new event comes a new set of people, a new set of faces, a new possibility for collaboration. At these events, we're not just there for an ego boost. We're there to network, find components, find other companies and organizations that have similar ideas to us, and have that initial spark which might lead to us collaborating and joining forces in our overall goal to net zero emission aviation. Now, coming back to our mission statement, to prove and promote liquid hydrogen as an alternative to conventional fuels in aviation. At this stage, promotion is in our blood. All of these events and all of these talks and collaborations have boosted our exposure in ways that we would not have seen coming. It seems every other week there is a new film crew at our office, filming and broadcasting what we're doing to national and international TV, widening our audience even further. The EU Citizens Prize, a prize that is awarded for international collaboration, was given to us over the last year for our efforts towards a sustainable aviation future. Now, focusing on the promotional aspect, our exposure has grown massively as well over the past year. And this is not just a stat that we can be proud of, but this really does lend, as you can see, directly into our mission statement. Our LinkedIn alone has grown by over 60% over the past year, opening our audience up to the whole world and to people that are not aware that you can use hydrogen in aviation, not aware that it's safe, and other queries that they've now come to the understanding after following our pages. Our goal was always to shake up the aviation industry, to kind of show that we can do crazy things as students, and if we can do it, why can the general industry not do it? And I think we can proudly say that today, that dream is already coming true. What started in 2018 by 2 ambitious students has now grown into something which we had never seen coming. which is AeroDelft as a key market player in the hydrogen aviation industry. And I'd like to also commend the industry as well. It seems over the past 1 to 2 years, huge amounts of money never seen before have flown into hydrogen, green hydrogen projects, infrastructure, sustainable aviation. This goes on and on. And this is a traditionally very slow industry, so to see it happen is really amazing. I'd also like to take this moment to thank our partners. Without our partners, none of this would have been possible. Now, if we partnered with you 3-4 years ago at our conception, or if we partnered with you last week, it doesn't matter. Every single one of you has been instrumental to the success that we've achieved here at AeroDelft, and we really look forward to working with you over the coming years. I'd like to give a round of applause on behalf of the whole of AeroDelft for all of your support and for believing in us. Right, now, back to some fun engineering. We started with a 1 to 3 scale prototype, and I think it's about time we see where we are with that.
Imagine the most dramatic HBO or Netflix series that you've watched in recent times. I can guarantee you, if you put 50 ambitious students together at the ripe age in their early 20s, working on such an ambitious project, you will get more drama, more ups, and more downs than you can imagine. My name is Aman Singhvi, and I'm the prototype technical manager of this year. Today with me, Gerben Drijfhout, our chief testing engineer, and Marius Klein, our chief propulsion engineer, will present to you the progress of our Phoenix prototype aircraft. Now, the Phoenix prototype exists primarily as a technological testbed to develop liquid hydrogen propulsion system. However, it also has a second purpose. It is the aircraft that has gotten our AeroDelft off the ground. It is the aircraft that has allowed us to build through these last few years and get to the stage that we are here today. AeroDelft started in 2018, and Project Phoenix started in 2019. In just 2 short years, we had our first big milestone. We managed to reveal the structure of our aircraft to the outside world. This year, we have focused on bringing the aircraft out of its construction phase and into its testing phase. In the coming years, we plan to intensify our focus on developing the hydrogen technologies that we aim to do at AeroDelft. Now, our goals are reflected in the way the prototype team is structured. We have a testing team focused on building and operating the aircraft, and we have a propulsion team focused on building, designing, and testing our propulsion system so it's ready to be integrated into the aircraft and validated in the air. However big our ambition is to decarbonize the aviation industry, we have to start small and we have to start simple. That is why the first step in the process is to fly our aircraft on battery power, to validate that the work done by the years before us has resulted in a flyable drone. After this, we can start increasing the complexity slightly and integrating our gaseous hydrogen systems. This includes our tank, a number of pressure controllers, and a fuel cell. Then we can take the ultimate step and fulfill the goal of Project Phoenix prototype, to fly on liquid hydrogen. This step, once again, increases the complexity even further, including challenges such as cryogenic storage, temperature control and pressure control, and conditioning hydrogen to be used in an aircraft. So where did we start this year? Well, our first task was actually rather mundane. it was setting up our workshop. While doing this, we moved countless testing rigs, materials, items, and we didn't really know what much of it was. This is an essential part of a student team working on a multi-year project. Every year at the start, there is a very steep learning curve in which the new team understands all the work that has been done by the past team. Without transfer of knowledge, a multi-year project like AeroDelft would not be able to progress. So, to introduce the aircraft is a 1:3 scale model of an E-Genius glider. It has a motor on the tail, and it's designed to be a glider to make the most of the precious hydrogen that we take with us on board. To give you an idea of its mass, it weighs about 45 kilograms. We have an operational empty weight of about 28 kilograms, giving us 17 kilograms to integrate our propulsion technology. Lastly, in cruise, to give you an idea, it uses about 1,200 watts, which is about equivalent to 20 household light bulbs. Diving deeper into the architecture of the aircraft, you can see here the system architecture of our liquid hydrogen setup, which is of course the end goal of Project Phoenix Prototype. In the front, we have our liquid hydrogen tank, followed by a number of pressure and temperature control components, behind which we have our fuel cell. Now, if a lot of you are overwhelmed or a bit confused by this picture, don't worry. Our chief testing engineer, Gerben Drijfhout, will now come on stage and break this aircraft down into smaller steps, just like we did at the start of the year, and explain how we set to work in achieving our goals this year.
Thank you, Aman, for the great introduction and showing us where we've come from with the prototype. And now you've all seen the previous slide with the very complex system architecture of what will eventually be our liquid hydrogen prototype. However, I'm going to try and break it down for you today so that we can all, in the end, understand what we're aiming for. Starting with the propeller and the motor at the back of the aircraft. It's meant to propel us forward so that we can make enough speed on the ground to get up in the air. This combination is fed by a speed controller. This controls the motor. And it's a very essential component in this whole system, and we really cannot do without it. This component needs its power from somewhere. So what we have in the aircraft is a set of batteries. These batteries are similar to your AA batteries at home, just a bit bigger and a bit more powerful. But of course, our goal is to fly on hydrogen. So what we need for that is a fuel cell, which is placed in the middle of our aircraft. So to just recap this quickly, what we have is a propeller that takes its power from a speed controller that is powered by two power systems. These two power systems combine their power through some complicated electronics that we're developing at AeroDelft. Now, this is the electric part of this whole system, but what we've not touched upon yet is the hydrogen part, which is of course most important. There are three main aspects to this. It's storage, temperature, and pressure. For storage of the liquid hydrogen on board, we have a cryogenic fuel tank right at the front of our aircraft in the canopy. The hydrogen that's being stored here is very cold, and to make it usable for the fuel cell, we first need to warm it up, for which we use a heat exchanger, which is positioned right behind the fuel tank. Now, to make sure that the hydrogen that's reaching the fuel cell is at the right pressure, we also have a set of valves to make sure that the hydrogen is conditioned well for use in the fuel cell. Now, as you see, it's quite complicated, and we're just going to run through it one more time from the back in just a bit of a different setting. Starting at the back, again, motor, speed controller, which take their power from batteries and a fuel cell that is combined in some power electronics. And the fuel cell takes its hydrogen from the cryogenic tank, which then feeds a heat exchanger and a set of valves. Now, this is very hard maybe to comprehend, and for an aircraft, it's a very complicated system to work with. And so over the years, what we've done at AeroDelft is try to boil it down to a simpler form so that it makes the goal of flying on liquid hydrogen achievable. So the first massive step we take in this is to go from liquid hydrogen to gaseous hydrogen. So we replace the whole right side of this diagram with a simple tank and pressure regulator, which reduces many parts in the aircraft and many interfaces. Now, of course, we're still dealing here with hydrogen and the complexity that comes with that. So, to imitate the fuel cell and make a representative aircraft for hydrogen flights, we replaced the fuel cell with another battery stack. And so this is what you'd call a battery aircraft configuration. We started the year off trying to make this fly for the first flight. But what we realized throughout the year is that this system actually inherits quite a bit of complexity from the hydrogen systems that were there before. And we don't necessarily need that for the first flight. So what we've done for our first flight attempt is to get rid of these 2 stacks of batteries and complicated power electronics and just put one there. So for the first flight attempt, we're left with this simple 3-way setup. Motor, speed controller, batteries. Really, really simple. To illustrate how much simpler it is than the liquid hydrogen system that we're working towards, let me show you this slide. We go from this amount of electronics and hydrogen components to that. And this is very important because the goal of our first flight is not to verify the powertrain. The goal is to verify that over the years at AeroDelft we built a credible aircraft that is able to fly well. And to achieve that, we faced some other challenges, of which I will talk a bit more now. Starting with the landing gear, then the braking system, and also the control actuators. So, starting with the main landing gear. Of course, we want to fly, but after you've flown, you also have to get back to the ground, and we want to do that safely. So what we need is a sturdy main landing gear. And building on the iterations that the previous team had made, we iterated twice further to get to a design that passed our tests and we thought would be ready for taxiing and eventually flight. The second system I want to touch upon is the braking system. Of course, again, we want to go fast, we want to go high, and we want to run over the entire runway with high speeds. But our runway is finite, and it's got cows at either end because we fly for Mark Nessa. So, we need a good braking system that's reliable. So what we've done over the last year is build on the components that the previous team had already selected. So we ended up with a hydraulic braking system powered by our little servos that I'll tell a bit more about in just a second. That got us to a point where we were comfortable with the braking system after countless hours of testing that we could safely stop the aircraft if we really had to. So coming back to control, like I said, we need reliable control in many different areas of the aircraft. We need the ailerons on both sides, the elevator at the back, the rudder at the back, and also the brakes. For all of these, we use what are called servos. These are tiny little motors that are very precise. And we started the year off with a very custom solution that was developed in-house by AeroDelft. And this would provide many great benefits, such as great flexibility and a lot of data gathering in flight. However, all of this customization meant also complexity. And what we realized throughout the year is that for our case, it was better to go with a very reliable and simple to use system. Eventually, we got to a point where we were very confident that all of these servos would actuate the way we wanted them to, and we could easily fine-tune their positions. So all of these developments got us to a point where we thought we would be ready for flight testing. Now, if we can get to the next slide, that would be great, which is not working on the clicker. There it is. So we got all of this progression on all these different systems behind us, and we thought we'd be ready for flight testing, and to tell you more about that, we'll get to it later in the presentation. But we first need to take a step back to see why we went all this way to get an operational aircraft. The goal of AeroDelft is not to fly on batteries, it's not the goal to essentially develop this plane, but the goal is to prove and promote liquid hydrogen as an alternative to conventional fuels in aviation. So in parallel to the work we've been doing at prototype testing, the prototype propulsion department has worked on all the hydrogen systems that we aim to fly on this aircraft in the future. And to tell you more about these systems, I'd like to invite our Chief Propulsion Engineer, Marnix Klein, onto the stage.
Thank you, Gerben. So, fuel cell technology seems like rather simple, right? To get from hydrogen to electricity. But the opposite is true. It's actually a rather new technology, and let alone in a plane, because how could we actually make it fly with it? Well, that's why we have to step back a little bit, of course. First, use gaseous hydrogen, because it's an off-the-shelf system. And then we can move on to liquid hydrogen. So, but why? Well, have a look at liquid hydrogen system first, right? Because, if our clicker works again. Yes. So, our liquid hydrogen system, it seems quite difficult, doesn't it? Because it is, actually. So, basically, we need to store liquid hydrogen. How do we store it? We need to store it at minus 253 degrees Celsius, which is really low, and it wants to heat up. So we have to keep it that low. But then again, we also need to control it to a usable temperature for our fuel cell. If the clicker works. We want to use it, we want to get a right temperature for it. And then at last, we also need a right pressure for the fuel cell, because it wants to operate in an optimal condition. That's why we first want to step back, use gaseous hydrogen first. An off-the-shelf system using only pressure control and basically as straightforward as it gets. So let's look at this gaseous hydrogen propulsion system first. Let's see what we did this year, actually, and what we achieved this year with the propulsion team and prototype. Well, let's look at the fuel cell. There's actually three main things that we focused on this year to get into flying, right? The first one is to actually meet the power requirements for the flight. We want to be able to turn right. We want to be able to climb as well. We don't want it to fail during flight, of course. The second one is actually environment, because our fuel cell is an air-cooled system. It actually, apart from electricity, it also produces heat. So we have to cool our fuel cell and basically have our environment ready for that. And that's quite hard in an airplane, because we have a quite small space, as you might see. And at last, we need to be able to integrate it in the aircraft as well. So integrate it with the electronics that exists already. So let's have a look at power first. We have our, as Gerben mentioned, our electrical setup. So our propeller, electronic speed controller, a motor. Those ones need to be compatible with our fuel cell. And we can only do so by testing. So we've done numerous tests with this, and we actually achieved a suitable system for this. And that means we know that we can climb in the aircraft. We know we can make a turn in the aircraft. Second point was environment. And environment is quite a tricky one because, as I said, it's the tight space in the aircraft that limits us a bit. And we need to find a way to still cool our fuel cell, because if it heats up, it doesn't perform that well anymore. And it might overheat. So let's think of a marathon runner. You don't want to overheat when you run a marathon. That's the same thing how the fuel cell doesn't want to overheat when it runs his. So that's why we designed cooling ducts for a system, to actually direct the airflow into the fuel cell while flying. And of course, as a prototype department, we have to test it as well. So we have done this using our very own test setup. Very professional. And we actually found that we can actually make sure that this works. But then, since we also go to the extremes by testing this, we got one setback. Our fuel cell started leaking. So we did leak tests on it, qualitative leak tests. We noticed small leakages all over. But as students, we won't be set back by this. So we started exploring its internals, learning from it, and actually seeing if we could use it still. We could still integrate it in our system. And eventually, after quantitative tests as well, we found that our performance of the fuel cell was still really good, that we still could use it in our aircraft, and that it was actually ready for integration. And that's when actually one thing is left, right? Integration. To get it actually in the aircraft, to make sure that the aircraft can perform well with all the electronics inside as well. And that's why I would like to invite Gerben on the stage as well to talk about this.
So as you can see, there has been a lot of work in both departments. But now it is finally time to marry the two departments together to perform our first ever full powertrain test. I'm going to take you through the steps we took to build up to that test at the end of our year and show you the results of that test. The challenge we face in merging the hydrogen system with our operational aircraft is power. Our fuel cell can provide 1.5 kilowatts of power, which is enough to keep us in the air. However, it is not nearly close enough to get us off the ground in the first place. So, what we need is to provide extra power, more than the fuel cell can deliver. And like I said earlier, for that we use batteries. Now we need to make these two power sources work together properly. And over the last few years in AeroDelft, a system was in development. It was named PowerPath. It essentially formed a switch between battery power and fuel cell power. So it would either run on the batteries or it would run on the fuel cell. Now what we realized this year, after facing many problems with this component, is that there is an easier way to achieve the same goal. So the naming department got out of their beds, went out of their way to come up with a new name for this incredible system. They went on hikes, did some meditation, some intermittent fasting, and they came up with the incredible name of the Lightning Line. Now, I'll take you through what that means in the next few slides. The realization came that you can place the battery stack and the fuel cell in parallel. This way, you can run on both systems simultaneously without issues. However, what this does cause is that during takeoff and cruise, most of the power is pulled from the batteries. So you're not taking full advantage of all the precious hydrogen you're taking on board. So the only system that we actually need to make sure that we can cruise on the fuel cell only is a simple switch on the battery line, to just switch the batteries off and fully fly on the fuel cell. Now, this is an integral part necessary for our full powertrain test. But to get to this point, we had to come a long way, because I'm not an electrical engineer, I'm an aerospace engineer. I like electronics, but I didn't have a clue about them, nor did the rest of our team. So we went through iterative design cycles where we learned step by step how to make these components, how to produce them, and how to test them. As you can see, we went from design to an integrated design to an even further developed design. And in the end, we had a component that was ready for the full powertrain test. Now, the full powertrain test is meant to simulate what happens in the aircraft. And when the system is on the ground, if my clicker would work again, that would be great. Again, thank you. So on the ground, it's easy to control all these systems pretty much by hand. You can monitor everything well, you can control everything well, but eventually we'll need to integrate this into the aircraft. So the system has to be somewhat autonomous. So in parallel to the development of the Lightning Line, we worked on the development of control systems to make sure that the switching and the fuel cell control can all be done remotely. So all this work from PT propulsion, prototype testing, culminated in this one day at NLR in Marknesse, where we aim to test our full powertrain. This would be the first time that AeroDelft would run a hybrid powertrain that would be capable of flying an aircraft. So the stakes were high. And as you can see on the slide, scorching heat, beaming sun, lots of pollen in the air. It was a harsh day, but we set up our full powertrain test and we aimed to do a full simulation of a flight profile. So with all systems ready and all systems checked, we turned off the propeller to simulate takeoff. So this is high power, high speeds, lots of wind going through your face. If the video plays. Exactly, there it goes. So you can see propeller spins up to takeoff speeds. You can hear the loud noises. It's quite a hectic environment when you're there. But after this takeoff, after the system has really been stretched, we get the time to do some checks while the vehicle is simulated to be in cruise phase. And we see that all our components are still performing normally, so we continue on the road of testing our full powertrain. To give our pilots some space in the air, we performed 4 missed landing attempts, which are very stressful for all the components because you have to power through the runway and gain altitude once again. But after these 4 missed landing attempts and stressing the system to its absolute limits, we still saw all the system performing normally. Nominally just means it's all good. So, finally we could simulate our descent phase, going down, back to the runway, safely on the ground. And this was a combination of massive efforts from previous year's teams, our team, 2 departments, and it was a giant success. But of course, we don't aim to fly on gaseous hydrogen. Once again, we have to stipulate that our end goal is to fly on liquid hydrogen. So, even though this is a great achievement, at the same time, we've been working towards that liquid hydrogen future. And to tell you more about all the liquid hydrogen developments that we've been making throughout the year, I'd like to re-invite Marnix onto the stage to tell you more about that.
Yes, so liquid hydrogen. As I mentioned, minus 253 degrees Celsius. That's really hard to sustain. So if we look back at our system, and we had the minus 253 degrees Celsius, the temperature control, and the pressure control. Those 3 components are actually very, 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 very hard to engineer, and even harder to integrate. So this is basically what we've been doing this year as well. And since this is what we've been doing, I'm going to talk about each component of these and dive deep into what we have achieved. So first off, our cryogenic storage tank. So, you can probably not hardly imagine, or maybe not imagine, how you can sustain minus 250 degrees Celsius of hydrogen. We actually do this by having a double-walled tank with vacuum insulation in between. So this is actually our own designed tank, and this year we have been able to manufacture it and also certify this production. The next steps are actually to leak test it. This will be taken on by next year's team. After those leak tests, we will be able to cryogenically test it, assemble it, integrate it further into our aircraft, and actually fly with it, of course. And speaking of that integration, I'm coming on to our next component. So our temperature control. How are we going to get this liquid hydrogen to make it gaseous, to actually be suitable, make it suitable for our fuel cell? Well, there's one simple solution, which is the heat exchanger. So we use actually heating tapes, active heating, insulation around it, to heat it up to above 0 degrees. And of course, we have to test it as a prototype department, as I mentioned before as well. So as you can see here, right, we tested our basically our connections in the heat exchanger first. And eventually that led us to the first ever cryogenic and functioning heat exchanger that we have in AeroDelft. So we actually made a proof of concept of this method. Yes, the video works. So as you can see here, we have liquid nitrogen. This is liquid nitrogen tested in our heat exchanger with gaseous nitrogen coming out. And it's really nice and big achievement for us because this is something we couldn't grasp on before. And now we actually have done cryogenic testing. So we know for sure that our system is going to work. It just takes a lot of testing, a lot of brains being shattered. And the last component is the pressure control system. So basically what we need to have is like a suitable pressure for a fuel cell. And apart from this, also overpressurization has to be prevented. So we have to get a safety line into that as well. And this year we actually have successfully assembled our pressure control system. And now it's actually ready for integration with our heat exchanger that I mentioned before, and also with our eventual cryogenic storage tank. But nothing of this is actually really relevant if we cannot fly our aircraft. So that's why I would like to invite Aman back on the stage to talk about this flight testing campaign that we are so excited to hear about.
So, there's not much point in having a fully tested, ready to integrate hydrogen propulsion system if you don't have an operational aircraft. This year, we carried out our first ever campaign at the NLR Drone Center in Marknesse. As you can see on the map, Marknesse is pretty far from Delft. So every single time we had to go there for a day of testing, we started our day at around 5:30 a.m. and didn't make it home any earlier than 8 o'clock. Our testing campaign spanned about 2 months and consisted of about 15 days in Marknesse in total. See it as a bit of a Sherlock Holmes mystery. During our testing, we were trying to identify and debug the issues in our aircraft that we found on the ground. We didn't have to find one, not two, not three, but 4 culprits in the end. So what did we have to improve? This can be broken down into the brakes, the firmware, the rudder, and the tail gear. In our first few days of testing, the taxiing was pretty rocky. As you'll see on the video I'm about to show, at just 6 meters per second, our aircraft would dart off in one direction as a result of the brakes being imbalanced.
5 meter per seconde. Stop. 6 meter per seconde.
Well, that's clearly not good enough. But on our first day of testing, it was all right. So we set to work on bleeding the brakes, recalibrating them, and working with the software, and eventually we got them working. The first challenge we overcame. Now, after this, we ran into our second challenge, our software. We noticed on the ground that, for no apparent reason, at some point, our rudder and elevator would simply stop reacting. You can liken that to, for example, if you're driving your car down the highway, and for some reason, your steering wheel just stops working. That's pretty disastrous. So we had to make a pretty drastic change. And the way we did this was to change the software we were using. We switched from PX4, Pixel software, to ArduPilot. This was a pretty difficult decision to make so late in the project, but it's one that we had to make. So the question that we got asked every single time we went to Marknesse, have you flown? Well, not yet. So we've had 6 days of testing now, and in every single day, we improved our aircraft a bit incrementally, but it still wasn't good enough. So we went back to the drawing board in Delft, and we decided we needed to increase the size of our rudder, based on the data we had observed. The reason we did this is by increasing the size of the rudder, you increase the amount of wind you can deflect, thus increasing the amount of force you have on the rudder, and giving you better ground control, which is the issue we were running into. Now, if you listen very carefully on this video, you'll notice something. And that is when you make one change on an aircraft, as is with all aerospace design, you run into 5 other things that change. So, if you listen very carefully to the propeller revving up, you'll notice the nose of the aircraft darts right. So, still not good enough. But once again, through observing the data, we learned a lot more. The propeller was creating a wash on the rudder. This meant, as you increase the propeller revs, the aircraft was forced to the right. So, at this point, we'd been in Marknesse, we'd done about 13 days of testing. And the question again that we'd been asked by our friends, family, anyone you can imagine, was actually, again, have you flown? And the answer was still, no. So we went back to the drawing board in Delft with dark clouds looming over our head. After 13 days, we were getting pretty demotivated, but we were definitely not going to give up. We decided to integrate a steerable tail gear, a pretty drastic change again, so late in our campaign. It was pretty difficult to integrate, seeing as there's a lot of fiddly electronics, a lot of fiddly structure things that you have to get into. However, in the next video, you'll see it got us taxiing much, much more controlled. This gave us a massive boost as a team. However, it was a bit bittersweet. At this point, after 13 days of testing, we heard that we only had 2 days of testing left. So we really were under pressure now as we headed off to our last 2 days in Marknesse. However, luckily, diamonds are created under pressure. And now it is my pleasure to share our first flight attempt.
Rudder, check. Ailerons, helemaal mooi.
AeroDelft is a student team of about 50 students working to prove and promote liquid hydrogen as an alternative to conventional fuels in the aviation industry. One of the ways we are doing this is by the creation of our prototype aircraft. Phoenix Prototype serves as a testbed for the novel propulsion technology we are developing together with our partners. The knowledge that we gain from conducting experiments will be crucial for our bigger, full-scale project that is also in the works. Today we are at the NLR in Marknesse to perform our maiden flight. You can tell that everyone here is a little bit nervous, but we're confident that it'll be a successful flight.
Our prototype aircraft has been in the making for over 2 years now. And as we started as a new team this year, we really tried to understand what the previous teams had already accomplished. We started by testing the subsystems of our aircraft, namely the brakes, making sure that we can brake properly on the runway. Also the control surfaces, making sure that we have reliable control in our flight. Bringing this all together here at NLR for these final testing days is very exciting. We are confident heading towards our first flight, and we're sure that it will be very successful.
congratulations on the first flight for AeroDelft. It was amazing today to finally see a very nice aircraft fly.
We've landed our plane. I'm massively proud of our team here today. We've worked many days and many nights to get this moment, and I can't say how proud I am of them. We're moving on with AeroDelft to improving and promoting hydrogen further, and hope to make our flights on gaseous hydrogen as soon as possible. So, to conclude, this has been one of the most successful years in the prototype project's history. We have successfully flown our aircraft on battery power, and what you just saw was the first time we have ever publicly shared photos and videos of this event. This proves that a student team really is capable of designing, building, testing, and successfully flying aircraft. This flight also gives us all the data we need to continue integrating our hydrogen propulsion system next year, and in parallel, also developing our liquid hydrogen components in the process. For now, I'd like to thank you all very kindly for your attention. We'll be taking a quick break where you can get a drink in the restaurant and let the photos and videos you've just seen sink in. Thank you.
All right, full scale. So now that we got the prototype flying, we basically got the perfect testbed to get comfortable with all our different hydrogen systems and also to get comfortable with hydrogen in a relatively safe environment. However, if we really want to prove that you can fly on hydrogen, we also need to fly with people on board. And that is why in 2020 the decision was made to start with the full-scale project. If I put it very simply, then the goal of the full-scale project is to transform a standard Sling-4 aircraft into a hydrogen electric variant. Once you complete the project, we'll be able to fly with 2 people on board for around 4 hours without any carbon emissions. But of course, before we get there, first a lot of steps need to be taken. So like I said, we started in 2020, so in the academic year before us. And during this year, really the foundation for the project was made. So most of the big components were selected, the sling was ordered, and also a preliminary design was made for most of the big components that needed to be designed. Therefore, when we got handed over the project in the summer of 2021, we really had a solid foundation for all the components that need to be designed. It was really sort of our responsibility to transform the full-scale project from something that was a design on paper to an actual physical object. Our goal for this year was to get the project out of the design phase, build the sling, and finish the electric part of the powertrain. After this, we will hand over the project to next year's team. They will continue with the development of the hydrogen part of the powertrain, test and verify it, and eventually also integrate it into the aircraft. We want to push for a first flight on gaseous hydrogen in the summer of 2024. After this, we will continue with the development of the liquid hydrogen system and finish the project hopefully in 2025 with the first flight on liquid hydrogen. But of course, before we can get there, we first need to do our part. And to do this, we've divided ourselves this year into 4 different departments. We've got the propulsion department, electronics and control, certification and testing, and of course, structures. Each of the departments all have their own different sub-projects, different sub-goals, and different timelines. And to explain this a little bit more into detail, I would like to hand over the word to the department chiefs, starting with our chief of propulsion, Joey Herbold.
Well, thank you, Rolf, for the great introduction. Indeed, I'm the Chief of Propulsion for the full-scale project. I want to take you over everything we learned in 1 year about our propulsion system. But today I only have around 10 minutes, so I want to give you a bit of structure to the story. And I want to take you back to what a fuel cell does, and fuel cell, of course, is the core of what we do. It takes oxygen and hydrogen into the fuel cell, and it converts it to electrical energy. This is the essence, and this is also what I will be talking about. There are a few subsystems to keep our fuel cell happy. The oxygen supply, the hydrogen supply, the electrical supply, the electrical load, and in any process you will see that there is a thermodynamic efficiency. So heat is also generated. We don't want overheating, so we also have a thermal management system. Well, these are the subsystems that we have, and I want to show you one more slide to just sum it up. So it's hydrogen, oxygen, thermal management, and an electrical load. Let's dive into the hydrogen part of what we designed this year. I want to go over 4 parts of this system, starting with the supply, from tank to fuel cell. In the aircraft, it will go from the tank to the fuel cell in the following route. But it's not as simple as just a supply. We have also designed a recirculation in order to improve the efficiency. Not all the hydrogen is used in the system, and we want to use the leftover hydrogen as well. So the recirculation comes out of the outlet of the fuel cell, gets recirculated through a pump, and back into the inlet of the fuel cell. This is how we supply everything, but we also need to take into account safety, especially when we will take passengers on board. So for the safety, one of the biggest risks is overpressurization. Kaboom, let's put it like that. So to prevent that, we have overpressurization venting line on the tank and on the pipelines themselves. And it will take a route like this. It will go to the back of the aircraft, and it will be vented out safely behind the aircraft. We have performed CFD analysis on the vent line and even took into account risks like combustion of the hydrogen when it leaves the aircraft. And we want to verify that none of the structural components or control elements of the aircraft are affected by such a potential flame. Then the last thing I want to cover, what is a system if there's no fuel in it? So we have a refueling system where of course also safety elements are present. We have check valves to limit blowback of hydrogen if the connection is interrupted. And we also have a filtering system to manage the purity of the hydrogen up to fuel cell level standards. This is, in the bird's eye view, our hydrogen subsystem that we designed this year. So then the counterpart in this whole reaction, oxygen. I want you to imagine that you are a particle of oxygen. You will enter the aircraft through an aqueduct on the side. We have guided airflow through a channel in the skin, which will take you to the piping system for the cathode side, the oxygen side. The oxygen is here conditioned to proper standards, just like the hydrogen. It is filtered, it is compressed, it's cooled, it's humidified, and it gets exhausted down through the aircraft. And of course, it has already been mentioned, but you will get water, H2O. Please don't drink it, it's not good for you, because there are no minerals in it. That is it for oxygen, but the thermal. I think this has been the most problematic subsystem in our design. Thermal management for fuel cells is a really hard topic, and that has mainly to do with the efficiency of a fuel cell. It's around 50%, which means that for a certain amount of energy from the hydrogen, around half of this will be produced into heat. For our system and our aircraft, this boils down to around 100 kilowatts of heat. And to put that into perspective and to make an analogy to houses like Aman did, that's around 10 households of heating. It's really a lot. And our solution to this problem, and it just fits, is a very big radiator. It takes around the entire surface area of the nose, and this really has been a struggle, but we made it work like this. We chose a very big radiator as opposed to smaller radiators in different cooling loops because we have limited space, and the extra piping that you would need would overcomplicate the nose. But combining everything comes with a few problems. You have components at 50 degrees, and you have components at 80 degrees. Of course, that will not really match if you combine that, because either one component is too low of a temperature, which would affect the efficiency of the component, or it would be too high and it would overheat. So to solve this, of course, it's all in the same loop, but to solve the issue of the 80 degrees, we have implemented a recirculation, which takes hot coolant from the fuel cell and reroutes it to the cold coolant that's coming in from the radiator, thus in effect mixing it to a lower temperature, which would suit the fuel cell as opposed to the compressor or any of the other parts. That's a little bit about the thermal. Please ask any questions you want because I don't have a lot of time. The electrical part is the last part. This is what drives the aircraft in the end. The fuel cell will power an electromotor with a propeller, as well as the compressor we mentioned before. So a bit like this. There is an issue here though. The compressor was used to give a supply of oxygen to the fuel cell. And the fuel cell gives a supply of electricity to the compressor. So you run into an issue, a circle of non-starting. So we need to break this, and therefore we also have batteries on board. We have a battery pack and a voltage booster to bring it to the same level as the fuel cell. And this will start our system and allow the operation cycle to start. We have worked with the electrical parts, so not the hydrogen, not the compressor, but the propeller and the batteries and the voltage booster. And we've gotten the hang of it, I will say. We worked a lot in the test bench, and we also started integrating this into the aircraft. And this really has been a valuable experience. Working with our hands, where the first 9 months of the year were spent on the computer, basically. We had a lot of fun. We built a very strong bond, I would say. I cannot thank the people I have worked with enough. And this is not solely a mission done by propulsion department, but also the electronics department helped out a lot with the control of the system, with all the low voltage cabling. And to explain more about this part, I want to give the word to Romy Haring, the Chief Electronics of the full-scale project.
As Joey has just shown, we have a fully working powertrain. However, we cannot safely fly an aircraft with only a powertrain. We also need to be able to monitor the aircraft to see what's happening. We also need to control the aircraft, and we need to distribute the power evenly. Well, that's where we, the electronics and control departments, come in. We actually started out as quite an inexperienced department, but with sheer enthusiasm and determination, we managed to create something to be proud of. So let's have a look at our first task, monitoring. As you can probably imagine, we try to design everything to work perfectly. But just in case something does go wrong, we want the pilot to be able to react immediately. For that, we want to have a monitoring display that shows all the most important values of the most important components. However, as you can probably imagine, you cannot simply buy a monitoring display for an aircraft that doesn't exist yet on the internet. So we tried to develop our own system. In the beginning, it had quite a lot of bugs. It's a bit like this clicker. Sometimes it works and sometimes it doesn't, but figuring out why it doesn't work is actually quite a hassle. But in the end, we did manage something to create. So this is our monitoring display. At the top, you see the values of the motor, for example, the rotations per minute and the temperature. In the middle, you see a schematic overview of our system during taxi. So we've got a battery, the voltage booster, the motor, and the avionics below it. It shows values like the power and temperature. At the bottom, we've got our error box, so that if something goes wrong, our pilot knows exactly what's happening within the aircraft. But how does this look like in the aircraft? So when we get our propeller spinning, we see our rotations per minute going up, and also our temperature goes up slightly. But because everything is in the green, our pilot has nothing to worry about. But still, on only a monitoring display, we still cannot fly. But the monitoring display gets its information via CAN. And CAN is a certain way of messaging. It sounds quite complicated, but it's actually quite simple. Basically, our modem sends out a message, say, "Hi, batteries." This message is obviously only meant for the batteries. So therefore, only the batteries will reply with a motor. Let's say, "Hi, motor." In a similar manner, our monitoring display gets its information from the power components. So let's have a look at our second task, control. For this, I want to take you into the cockpit. This is what the pilot sees when he or she is in the cockpit. You have, for example, the primary flight display. This shows you how fast you're going and how high you're flying. We've got a radio to communicate to the ground, a transponder to transpond our location, and this thing all the way on the right is what we call our glove box. It houses all the important connectors and board computers that are easily accessible for the engineers to make some last-minute tweaks. There are a lot of components on the dashboard, but believe me when I say there are even more components behind it to get it all working. And installing them was quite a hassle. We tried to test and install as much components as possible before putting it into the aircraft, because to get some familiarity with the system, but also because there's limited space inside the aircraft. And we've got a lot of components, a lot of departments, and a lot of people wanting to work in the thing at the same time. So that led to a lot of cables, all with their own function and a tendency to get tangled. I especially remember one Saturday working with Nanami, where we basically found out that our arms are always too short and our bodies too inflexible to reach all the places that we needed to reach. We went home that day with sore backs, but the looks on our faces after our first successful small test were priceless and definitely worth it. So we've got a lot of components installed now, but where do they get their power from? That brings us to power distribution. Let's take a look, for example, at the dashboard. We've already seen one powertrain, which is from the batteries to our voltage booster to the motor. However, this high voltage power system, we only want to start up while monitoring it. So we have a low voltage battery that provides power to our dashboard. When we see that everything is good, we give some low voltage power to our powertrain components, and when everything is good, we can get the thing rolling. We tap off a little bit of power and boost it down to recharge our low voltage battery so that our low voltage battery can remain, well, small. That were basically our tasks, so to monitor, to control, and to distribute the power well. But let's have a look now at a department that's often overlooked, but just as important, namely showing the authorities that what we're doing well, and that our aircraft is safe to fly. For that, I'd like to give the floor to Vlad, our certification officer.
Hello. Thank you, Romy, for the introduction. Now I'd like to talk about certification and why it's needed and how we can go about achieving it. On average, there are around 10,000 planes carrying more than 1 people in the air at any given time. Despite this, aviation is by far the safest means of transportation out there. This can only be achieved through the strict rules and regulations every plane needs to adhere to. This is where certification comes in, identifying possible risks and establishing mitigating measures to prevent them. In our case, we are taking a Sling 4 aircraft and converting it to hydrogen propulsion. As we are trying to fly in the Netherlands, which is part of the European Union, we need to certify with the European Aviation Safety Agency, or EASA. As we are building a single airframe, which will be very closely monitored and whose only purpose is to prove flight on liquid hydrogen possible, we claim our aircraft is experimental. This means we won't have to deal directly with the EASA, who are very strict and constantly occupied. We will have to justify our aircraft's safety to the Dutch civil aviation authorities, the ALNT. The Dutch government is currently working on an experimental aviation law, which will make the entire certification process much easier. But currently, that law is still not yet developed, so we still have to deal with. So the authorities, in the meantime, will tell us to follow the EASA certifications. This is the certification specification for normal category airplanes, CS23. While we still have to adhere to EASA regulations, the Dutch authorities are willing to work with us and help us achieve flight easier. They are willing to reduce some of the requirements placed on us, especially with regards to service life. So how do we go about achieving certification? This is where the design and certification plan comes in, the big document required by us. It contains everything required to obtain certification license for the aircraft. Some of its items include the CS23 requirements and our means of compliance to them, an introduction to the AeroDelft team, data on our performance before and after the changes we are making to the aircraft, our partners who are helping us and how they're doing that, a planned schedule for the entire AeroDelft project, design data for all of the components that are going into the aircraft, test reports and other performance reports of all of our components, and analyses of these reports in order to justify safety. The most important of these analyses is this safety assessment. As a lot of the components going into the aircraft are made by AeroDelft, with the propulsion system being entirely new in aviation, we need to make sure they are 100% safe. This is where the safety assessment comes in. It looks at everything from the top down to the bottom and bottom up to identify all possible failures in the aircraft. The aircraft level safety assessment looks at functions inherent to aircraft, such as thrust, lift, control, etc. It looks at those functions and points to the system level safety assessment as the possible cause of their failures. The system level safety assessment looks at, does basically just the same thing, only pointing to individual components that can cause functional system failures. The item level safety assessment looks at the aircraft from the bottom up. It looks at each individual component, how it can fail, and what its failure can determine. So how does this actually play out to us? For example, we take a failure of failure to control thrust in the air. This can be determined by the failure of the system function provide cruise power. That, in turn, can be caused by a DC-DC converter failure. And that DC-DC converter failure could be just the component itself failing. On the other hand, a battery failure could manifest as a fire, which could actually damage the DC-DC converter due to their proximity in the nose of the aircraft. Looking at the entire system in this manner lets us identify any and all possible failure scenarios. But that is not enough to justify safety. We need to prove that these failures won't come to be, which requires testing. Testing is the only reliable way to figure out how everything in the aircraft will actually work out. Because no matter how smart the engineers designing the systems are, nothing will work out quite as they expected, quite as in their calculations or even in their simulations. Testing serves as the main means of justifying safety, as it will identify all failure scenarios, their causes and effects. And of course, we would have nothing to do, nothing to test, without the work put in by the amazing structures department. So let's hear all about it from Tetsuo.
All right, thank you, Vlad. So structurally, there are two main challenges to overcome when it comes to converting our Sling 4 into a hydrogen-powered airplane. First, it's designed to fly on petrol, and not on hydrogen, of course. So how do we integrate all the systems mentioned by Romy, Joey, and Vlad without compromising on safety and performance? And second, it's a kit aircraft, which means we have to build it ourselves. Overcoming these two challenges has formed the foundation for the way this year's structures department was organized. It was our task and responsibility to make the necessary modifications to the original structure and to ensure the structural integrity of our aircraft. But first, I would like to talk a bit more on the modifications that we worked on this year. So, this year we worked mainly on 4 modifications to make our airplane fly safely on hydrogen. First, a custom motor mount. A custom motor mount to support our electric motor and batteries. Second, a mounting structure to attach our hydrogen system to the airframe. Third, a ventilation system to circulate air around hydrogen-carrying components to prevent buildups of hydrogen in the event of a leak. And last, a firewall to protect the passengers in case of a hydrogen fire and to act as a wall on which we can attach components such as an air filter. I could and I would spend hours talking about the engineering work that went into all of these 4 subsystems, but due to limited time, I will only dive deeper into the design process of our custom motor mount. This way, I want to give some insight in the way we handle complex engineering problems like these, and to show you how we design our customized parts such that they are safe to use in our aircraft. But first, we need to establish why we need a custom motor mount in the first place. Why can't we just use the one that comes with the standard Sling 4? So on this slide, I've put the original combustion engine that comes with the Sling 4 next to the electric motor that we use. And here you can already see that they are inherently different in their size, weight, and shape. And thus, each needs their own custom motor mount. So, to give an example, our electric motor is much shorter than the original combustion engine that is in the Sling 4. Given the fact that the propeller is in a fixed position, we need a motor mount that extends way more to the front. Now, with our electric motor in position, we can add other components from the powertrain, such as the batteries and the radiator, to end up with this final configuration. Now, before we can make this motor mount, we have to get an idea or better understanding of its strength by performing finite element analysis. Using special software, we can get an estimation of the peak stresses and deflections that could occur during various flight cases, which we derive from the certification requirements. After doing countless iterations, which if you ask Susanne is an understatement, I think, we judged this motor mount to be strong enough and ready for manufacturing. So we chose a high-strength steel for our motor mount, and after we ordered the tubes, we had them cut to length and angle in a mill at the TU Delft. Then it was time to weld the tubes together to make our motor mount. This proved to be a tricky task, but Susanne, Pepijn, and Niels managed to weld the tubes together using 3D printed jigs. And here you can see a photo of Susanne and Niels working on the motor mount. And here is a photo of them looking at analyzing a weld after it is finished. So now with our custom motor mount welded, it is time to install it on our aircraft. Making modifications like these can be scary sometimes, especially when the life of a human is at stake. Unfortunately, this responsibility holds even more when you want to build an aircraft. So now I would like to take you on our journey of building a Sling 4. So, thanks to the efforts of last year's team, our kit arrived last August in the aircraft hall at the TU Delft. Our hands were itching to start the building process, but we had no clue on how to start building. So that's why we did some research, and we concluded that we needed to organize 3 essential things before we could start building. First, we needed a clean and organized workshop. Second, we needed to collect tools, such as rivet guns and drills, but also more exotic tools, such as a safety wire twister plier. And lastly, and maybe more importantly, we needed some guidance and expertise to teach us the fine skills of building an aircraft. And this we found in the Dutch Association for Amateur Aircraft Builders, or in Dutch the NVFA, and the technicians working at the aircraft hall, and later also the people from Vision Air who sponsor our project. So that is not, we organized these 3 things, but that was not the entire story, of course, because some people in our team had never even used a handrail before. So we made these practice toolboxes to gain familiarity with the tools that would later become extensions of our bodies. Now, excited but cautious, we made a beginning on our very first of many assemblies, which was the tail. This is a relatively simple assembly, but it covers most of the standard practices that you will need during the entire building process. So building this assembly helped tremendously in gaining the necessary confidence that we needed to handle the aircraft parts, and within a few weeks we had actually finished our first aircraft parts. So here you can see a finished rudder and vertical tail, and on the right you can see the horizontal stabilizer. So at the beginning of the year we set a painting deadline in June, and knowing how much work still needed to be done to make that deadline, we could often be found working in the evenings or even on holidays, which took quite a heavy toll on the team, I think, but we were really determined to make that painting deadline. So fast forward to March, with the tail finished and the right wing also finished, we were putting on the fuel tank on our left wing. And with the experience from the right wing, we thought it would go smoothly again this time. But at this moment, we encountered probably the biggest setback of our year. Our fuel tank would not fit on our left wing due to a production error in the main spar of our left wing. The main spar is basically the backbone of your wing, so we contacted the manufacturer and they gladly offered to send a completely new left wing to us. This was a huge relief, but we had just spent the last 4 weeks of building on a wing that is basically useless to our aircraft. And we also didn't know if this wing would even arrive on time for the painting deadline in June. But accepting the situation as it was, we decided that this wing could maybe be used by future teams as a testbed and experimentation for example, putting batteries in a wing. So we kept on going, and with risking our own lives in the following months, we glued in the canopy, we made the landing gear, and we did some more work on the fuselage. It really started to look like an aircraft at this time. So, on May 30th, it was time to transport our aircraft to the paint shop. This was quite a scary but exciting endeavor, but with the help of our friendly truck driver Frank, we managed to get the aircraft safely to the paint shop where we could spend the next 2 weeks painting it. So, with the help of our teammates from other departments and the left wing arriving just in time, we managed to finish the job on the last day. And this was also a huge moment of relief. So, after the weekend, we brought the aircraft back to Delft, where we spent the following 4 weeks, up until today, trying to finish the last things that needed to be done. It was a huge privilege for our team to have the opportunity to build an aircraft like this. We gained so much experience that is invaluable to us, and we made many happy memories together that are unforgettable. So now I would like to end my presentation with 4 facts and figures that I think summarize our year of building a sling. We have broken at least 3 rivet guns. We have pulled more than 10,000 rivets. We have made 3 wings for a 2-wing aircraft. And we all found our new retirement hobby. So now I would like to hand over the words to Rolf again, who will wrap up this presentation.
right. Thank you, Ted. I think from the presentation you already got the impression, but it really was a busy year. We had a lot of ups and also a lot of downs. All in all, I think this year really serves as a really nice example of how much you can accomplish when you work together as a team. And I therefore also feel like we should close the presentation together with the team, and I would like to ask the team to come up with me to the stage. Ladies and gentlemen, in a bit, the doors behind you will open. I would like to ask you to go outside and spread yourselves among the fans to enjoy the view. Please turn around. This is the Phoenix full scale. You can go outside and spread across the fence.
Look at them yo-yos, that's the way you do it. You play the guitar on the MTV. That ain't working, that's the way you do it. Money for nothing and your chicks